Okay, so today we are going to finish the topic of high-dimensional linear regression. So last time we introduced the lasso method, which is a convex algorithm that is computationally efficient to solve the sparse linear regression problem with nearly optimal convergence rate. Let's first review the result of lasso that we have learned in the last lecture. So our setting is a Gaussian linear model. So Y follows a multivariate Gaussian distribution with mean vector x beta covariance matrix given by sigma squared times identity. So the dimension of the response is n. The design matrix has dimension n by p, and therefore our goal is trying to recover the regression vector, which is of dimension p. Okay, so we assume that beta is a sparse. Okay, so by sparse, we mean is beta as a vector of p dimension has only a few number of entries that are non-zero. They can be, for most of entries, they can be exactly zero, or they can be approximately zero, right? So one can be characterized by the value of the L0 norm. The other can be characterized by the value of the L1 norm. Okay, so the lasso algorithm optimizes the following problem. So what is lasso? It is defined as the global minimizer of the penalized least square problem, and the penalty is given by the L1 norm of the regression coefficient. So if you can solve that, we then proved a theorem in the last few lectures. Says if we assume that each column of the design matrix is bounded by some constant L times root n. So each column's the L2 norm is of order root n for some constant L. Right? Then we can choose lambda to be some constant c times sigma, which is the noise level, times root n log p for some large constant c. Okay. We then have the following risk bound. The error bound, which is for the prediction loss. It will be bounded by one of the two terms. The first term is an error bound given by the L0 norm of the regression coefficient. And the second term is characterized by the L1 norm of the regression coefficient. Okay? And moreover, for the estimation error, which is the error for beta directly, that's just the prediction error divided by another factor of kappa squared. Right, so what is kappa? Well, kappa is called the restricted eigen value. This is defined to be the usual definition of the smallest eigenvalue of the sample covariance matrix but with additional constraint that the minimization is taken over a cone, because we can prove that for lasso, the error vector must be an element of the cone. Okay, so this is the result that we have proved in the last few lectures. And we also mentioned that the rate with respect to the L1 norm, this guy is the minimax rate. This is minimax optimal with respect to the parameter space characterized by an L1 ball. For the first rate, this is the near minimax rate for the L0 norm parameter space because of the extra kappa squared, right? So without kappa squared, this is going to be almost the minimax rate for the L0 parameter space. So today, let's talk about some of the important extensions of the lasso algorithm, what people use in the literature to solve sparse linear regression is not just restricted to the lasso algorithm. There are many other high-dimensional sparse linear regression methods that are also very popular. Okay, and one of the methods that we have already mentioned is L0 penalty. So let's talk about extensions and improvements. So the first method is called L0 penalty. We have already discussed L0 penalty, and in particular, AIC, BIC are special cases of this method. And in particular, if we use the complexity penalty, which is a function of the L0 norm of the regression coefficient proposed by Béger and Massot, then we are going to achieve the exact minimax rate in terms of the L0 norm of the regression coefficient. Right? It's going to achieve the optimal rate. S log EP over S, then over N. Okay. However, we know that this L0 penalty method cannot be computed. It is basically NP hard, right? And not only that, we have also mentioned a computationally lower bound algorithm by John, Wainwright, and Jordan, which says that there is no polynomial algorithm that can achieve this rate. Okay, so not just you cannot achieve this rate by lasso, but any efficient algorithm cannot achieve this rate. There is an intrinsic computational barrier. So the second method, this is, for example, non-convex penalty. So this is also penalized least squared with a general penalty function. Okay, so what is this idea, right? So the idea is motivated from a critical drawback of the L1 method. So let me first remind you of the shrinkage operator of the L1 penalty, right? So we have mentioned last time, if we have Y, then for the orthogonal design, basically the L1 penalized least square method give you the soft thresholding solution, okay? So this is arg min Y minus B squared plus lambda absolute value of B, right? So the one-dimensional version of the linear regression problem. So what it does is hard thresholding. Okay, so if this is the function y, right? So this is the 45-degree line. And then what the soft thresholding function does is to pull the data y towards 0. Right? So as long as its absolute value is bounded between some interval, then the solution is going to be exactly 0. Otherwise, it's going to be shifted by some constant. Now, what is important is no matter how large y is, it's always going to be shifted by the same amount, right? Basically, by the order of lambda. This is O lambda. Okay? So even if, for example, y is 2 million, right? You know it is impossible that the regression coefficient is 0, but Lasso is still going to output with you a solution that is biased, right? So this constant bias problem is going to make Lasso, which is not very good for coefficients that are very large, right? So in order to reduce the bias problem, people actually study new penalties. So the penalty that people study look like this, right? So first of all, it's obvious that below a certain level, you still need to threshold everything to 0, right? So this creates sparsity. However, as the value of y gets larger, you should gradually decrease the bias resulted by the thresholding or shrinkage operator. Okay? And you can actually design a specific penalty function so that it achieves this effect. Right? So a special case is the L0 penalty. Right? So what is the L0 penalty? The L0 penalty is called hard thresholding. So this is L0 penalty. Okay? This is L0. So what L0 does is called hard thresholding. Which means if the value of y is below a certain threshold, then you threshold it to 0. Otherwise, you just output the original value of y. However, what makes L0 penalty not computable, right? So it is not it cannot be computed, is because the induced shrinkage operator, which is the hard threshold operator, is not continuous. Okay, so we can actually design a penalty function whose the shrinkage operator is continuous. Okay, we have several candidates of such penalty function in the literature. The two famous options is called SCAT, the SCAT penalty. SCAT is proposed by Jianqing Fan, who has also received the COPS award, and his student Renze Li. Renze Li was one of the previous editor of the Annals of Statistics. And also MCP, the MCP penalty. This is proposed by Kanghui Zhang. Okay, so I'm not going to write down the exact formula for these two penalties, but in the homework, you will be able to read the paper, the original paper, which proposed these two penalty functions. Okay, and in fact, if you use these penalty functions, you can achieve a better risk behavior compared to Lasso. All right, so if you use for SCAT or MCP, you can show that the prediction loss can be bounded by sigma square S1 plus S2 log P over n kappa square. Kappa square is still the restricted eigenvalue. But what is S1 and S2? Well, S1 is the cardinality of the coordinates whose value of the coefficient is greater than some constant times root log P. S2 is the cardinality of the coefficient that is not zero, but its magnitude is bounded by some constant times root log P, right? So if you calculate S1 plus S2, you can call it S. That is the sparsity of the regression coefficient. So basically, S1 is the number of large coefficients. S2 is the number of small coefficients, right? And here you observe that you only multiply S2 by a logarithmic factor of the ambient dimension, right? Because S2 is those small coefficient, which is of order root log P of n. So this is where it is really hard to distinguish between 0 and non-zero, right? Therefore, you have to pay a logarithmic cost in order to achieve the optimum rate. For those regression coefficient that are large, there is no uncertainty. You don't have to pay the logarithmic price, right? You can achieve the parametric rate. Okay, so if you compare this rate of convergence to the one achieved by Lasso basically has S1 plus S2, the entire sparsity times log P, right? So the improvement is exactly a consequence from using a penalty function that corrects the bias problem of Lasso. So the third improvement is given by a method called slope. This is another penalty function. So it is proposed by a paper written by 5 people. Bogdan, Vandenberg, Chiara Sabati, Weijie Su, and Emmanuel Candice. Right, so you have already known Emmanuel Candice, who is the advisor of Rina Barber, and the famous paper of Candice and Tao propose Danzig selector estimator, which achieves the near minimax rate with a polynomial time algorithm, first in the history. Right, so this is a paper that actually studies a different penalty function. So Chiara Sabati is Emmanuel Candice's wife, and Weijie Su is Candice's student. And these 2 people are from Europe, so I guess at that time they happened to be visitors at Stanford. Okay, so what's the motivation of slope? Right, so this is really a very subtle motivation. If you look at the optimal rate achieved by the L0 penalty, then you see in the recursive factor you have log P of S. Right, so this is actually very nice. When the sparsity is just a P, then log P over P is a constant. The rate is reduced to the parametric rate. However, for the Lasso estimator, it only has log P. Right, it would be nice to achieve log P over S. And actually, a slope is an estimator that achieves this slight improvement of Lasso. Which is sigma squared S EP over S over n kappa squared. right? So you actually achieve this improvement by using the slope estimator. So the exact form of the slope estimator is complicated, but basically it can also be written as a form of the L1 penalty, but actually a weighted form of the L1. Okay, so this notation means you actually you order the absolute value of the vector beta according to its magnitude, right? So you want to order the absolute value of each coefficient from the largest to the smallest. And then the idea is you give different weights to coefficients with different magnitude. The reason this works is because this type of penalty has an intrinsic link to false discovery rate control in multiple hypothesis tests. Okay, and such a link was previously discovered by a very famous paper by Abramovich, Benjamini, Donahoe, and Johnston, and somehow they formalized at the slope so that they can apply the same idea to the regression problem. All right, so the last improvement or extension I want to talk about actually has two names. This is two methods, but these two methods are equivalent. One is called scaled lasso. The other is called square root lasso. So these two methods are proposed around the same time in the literature, and then and very shortly people discovered actually they are the same methods. So this, the first method is proposed by Ting-Ni Sun and Kanghui Zhang. So Sun is Kanghui's student. The square root lasso is proposed by Beloni, Chernodrukov, and Wang. Okay, so Chernodrukov is probably the most productive econometrician in the world. He is a professor at MIT, and Wang he was a PhD student of Tony Kai in Wharton, and after he graduated, he joined MIT as a assistant professor, but now he went to industry. Okay, so what do they want to improve? Well, here is another problem with lasso, right? So we see a lasso actually has lots of problems that can be improved. Is this problem, right? So you have to choose the penalty level lambda proportional to the value of the standard deviation of the noise. Okay, so this choice will give you theoretically the best performance in terms of the error bound. However, in practice, you do not know sigma, and it is really hard to estimate sigma in a high-dimensional setting. So what if we do not know sigma? Is it possible to still achieve a good rate of convergence with a different method? Well, this is the motivation of scaled lasso. So scaled lasso works with a different penalty. Different objective function. So the objective function is a joint function of beta, the regression coefficient, and sigma, the standard deviation. It is defined in this way. Now, there are several properties of this function. So first of all, this is a convex function. Not only it is convex in beta, it is convex in sigma, but it is actually jointly convex in both beta and sigma, right? So if you optimize over this function, you are going to achieve the global minimum. And in fact, you can iteratively optimize over beta and sigma. Okay, so the algorithm is you first update beta by fixing sigma, and then you update your sigma by fixing beta from the previous step. Okay, and since the objective function is jointly convex, this is going to converge. All right, and the first step is actually just a lasso problem, right? You see? So the first step is going to optimize over beta, but this term is independent of beta, so it's just the optimize over this guy plus this guy, right? Which can be equivalently written as the L2 norm squared plus lambda sigma L1. Okay, so I multiply sigma on the objective function, so the minimizer is not changed, right? And for the second term, that's just a one-dimensional optimization problem, right? So you optimize over the first two terms. Okay, just take derivative and set to 0, or for some of you who are quick, you can probably already see the answers. So the answer is going to be given by the residual. Right, of course, this is the beta is from the previous step, and sigma is also from the previous step. Okay, so the second step has a closed formula. Right, so it is very intuitive. You estimate the sigma squared by the residual, and then you plug this sigma into the penalty level. And since what we need is lambda to be proportional to sigma, so with an extra sigma, we can just choose lambda free of sigma, right? So even if you do not know sigma or even its order, you can still use scale lasso to achieve the good property of the lasso estimator. But what is square root lasso, right? So square root lasso actually deal with this objective function. Okay, let's call it g of beta. Right, so if you minimize over a sigma, then you can actually obtain a new objective function like this, right? So if you do that, basically it's equivalent to have the square root of the least square objective plus some number times the L1 norm. So why is this true? Well, if you optimize over sigma, then sigma takes this form, right? You're plugging this form into the original objective function, right? So this is the L2 norm squared. So it's going to give you the square root of the L2 norm, which is L2 norm squared, which is the L2 norm, right? That's why it's called square root lasso, right? So these three people said that when you minimize over the lasso objective, you do not need to square the objective of the first term. If you don't do that, then that will give you an estimator that is adaptive to the unknown noise level. And it turns out these two methods are exactly the same because of this relation, right? Okay, so as you can see, lasso has a lot of drawbacks. Don't get me wrong, it is a very good estimator, has these great error bounds, but you can certainly improve the performance of lasso from various perspectives. And actually, you can even combine some of the improvements to create new methods. So I'm not going to go into details here. Okay, so now the last topic about high-dimensional linear regression is Bayes methods. So let's spend a few minutes talk about Bayesian sparse linear regression. Now, even though the frequentist methods have very good properties, so for all these methods I just listed, you have great theoretical justifications proved by these people with good mathematical skills in the literature. Usually, Bayesian methods do not have a theory, but it turns out the best method that works in terms of numerical experiment is the Bayesian methods. Okay, so first of all, I want to briefly talk about you can actually view the Lasso method as a Bayesian method, right? So the Lasso actually work with the sum of these two functions, and the first function is the negative log likelihood. So you can also write Lasso estimator as argmax beta, then e to the negative 1 over 2 y minus x beta, then minus the penalty function. Okay, maybe I should write negative 1 over 2 sigma squared, right? So you can write it in an equivalent way for the Lasso estimator. Then if you look at the first term, this is going to be the likelihood of the data generating process, right? So you can actually view the L1 penalty as a Laplace prior put on the regression coefficient, and the Lasso estimator can be viewed as a posterior mode for this posterior distribution induced by the Bayes formula. However, this is not really a Bayesian method, right? This has a Bayesian interpretation. The posterior itself is not very good. I want to claim that this is a useless posterior. Okay? So the only thing that is good about the posterior is the posterior mode, which is the Lasso estimator. If you don't compute the posterior mode, for example, you apply MC algorithm to sample from the posterior distribution, or if you just compute the posterior mean, then it will give you rubbish. Okay? The reason is, even though the L1 penalty encourages sparsity, but as a prior distribution, the corresponding Laplace prior does not encourage sparsity. Right? Laplace prior, if you sample from it, it will give you dense random samples. As a result, the posterior is also a dense distribution, right? So if you can sample from the posterior induced by the Lasso, you won't get any sparse samples. All the samples you get from your MC algorithms or Gibbs sampling methods are going to be dense. Right? It's just the dense estimator. The only estimator you can extract from the posterior, which is sparse, is the posterior mode. But that's it. So Lasso is really bad if you want to view it as a Bayesian way. So the question is there a prior distribution so that the induced posterior distribution has optimal rate of convergence, in the sense that if you sample from that posterior, it will give you the minimax rate performance. Okay, so this turns out to be an open problem for a long time, but it actually it's solved by my paper. So this is my paper with Van der Waart and Harrison Zhou. I did this work when I visited Van der Waart at Leiden University when I was a PhD student. So here's our prior distribution. Okay, so the likelihood is the Gaussian model, Gaussian linear model. The prior distribution, let's call it pi, is specified by the following sampling process. Okay, so the prior is actually hard to describe. Therefore, let me tell you how I can sample from the prior distribution. Right? If I tell you how to sample from the distribution, then this is equivalent to tell you the distribution itself. So first, you sample S from some probability mass function supported on 1 to p, right? So you sample a number, a random number from 1 to p, and this is going to be the prior sparsity, the sparsity into the prior. And I choose this probability mass function to be proportional to e to the negative some constant times s log ep over s. This is the first factor. And the second factor is the ratio between two gamma functions, gamma s and gamma s over 2. I'm going to tell you why this is actually the correct choice. Now the second step is given s, right? I already have the sparsity. I'm going to sample the support of the regression coefficient. Sample s to be a subset of 1 to p uniformly over all subsets such that the cardinality is S. Okay? Now, the last step, right? Given a small s and a big S, now I can sample my beta, right? So I'm going to let beta to consist of two parts, beta sub s and beta sub s complement. And here, beta sub s complement is going to be set as 0, right? So I'm only going to allow non-zero entries appear on the coordinates in S that I sample from the second step. Okay, and I sample this guy from a distribution that is proportional to e to the power of negative lambda. Again, lambda is a constant, times the L2 norm of x sub s beta sub s. All right, so here x sub s is an m by s design matrix, which is a submatrix of the original m by p design matrix. Just to take those s columns in this set, and then beta s is a subvector of the entire beta, right? So I'm going to sample the non-zero part from this distribution, and the zero part just set it to 0. Okay. So notice that I do not have a square here, right? So this is not a Gaussian distribution. This is called an elliptical Laplace distribution. Okay? So now, this is my entire prior distribution. How do you sample beta from the prior? Well, this is your sampling algorithm. Okay, so this defines a prior distribution. It is guaranteed to be sparse because it is sparse. Okay, and why it works? First of all, what do I mean by works? So here's the theorem. So the theorem that we prove is that the posterior probability now I need to make a few notes. So beta star is the truth. Okay, that's the true regression coefficient, and beta is under the posterior. Okay, so this beta is random, is distributed according to the posterior distribution. And this is the truth that I'm going to, that generates the data, right? So I'm looking at the error under the posterior distribution. So the error greater than some constant. So this is the different constant. Let's call it C tilde, right? Just to distinguish from this constant. They are irrelevant. Some constant times sigma squared S log EP over S. Now I should put S star here, right? So because this is not a generic S under the prior, but here this S is going to be the sparsity of the true beta, right? So that's the L0 norm of beta star. Now the posterior probability greater than this guy, given data is Y, converges to 0. This is improbability. Okay, so here's the result. The result says that if I can sample from the posterior using MCMC, then with high probability, the sample I get will have the property such that the random beta that I sample from the posterior, if you look at the prediction loss, it's going to be smaller than this number, right? So any sample you get from the posterior is going to be minimax optimal, achieves the minimax rate. Okay, this is exactly what you can achieve by the L0 method, right? And in fact, the method that we design here can be viewed as a Bayesian counterpart of the complexity penalized method introduced by Berger and Massat, right? So if you remember the L0 method by Berger and Massat, what they did is to use S log EP over S as your penalty, right? As their penalty to achieve the optimal minimax rate. So here, the intuition is whatever penalty you can use in the frequentist literature, you take exponential, then it can be viewed as a prior distribution, right? In the same way, I take this factor to be my prior distribution on sparsity, right? However, why do I have this extra factor, right? This is mysterious. Why do I have this guy, right? This can be easily understood because this is the minimax rate. You want to put smaller prior weights on larger models, right? This is obvious, but why do you have to do this, right? So this actually comes from the consequence that I use a multivariate elliptical Laplace distribution in the prior distribution of the non-zero regression coefficients. But first, why do I have to use the Laplace distribution? Is it possible that I just use a Gaussian distribution? Well, it is impossible, right? Because I remember it is in your homework 1, right? In your homework 1, that even for the one-dimensional normal mean estimation problem, then you just put a conjugate Gaussian prior distribution on your normal mean. You compute the posterior mean, the maximum risk will be infinity. Right? If you don't know what I'm talking about, you should check the solutions to your homework 1 again. Right? So the worst case risk of the Bayes estimator induced by the Gaussian prior is infinite. Okay, this is because a Gaussian prior has a very light tail, so it is actually a very strong prior knowledge. In a sense, if the true regression coefficient is very, very large, then you are going to have an arbitrary large error because of the unnecessary shrinkage. Therefore, we have to use a heavy tail distribution here, right? So you can use Cauchy, for example, but Cauchy is going to work, but overkills. Turns out, as long as the tail is as heavy as Laplace, it will work. Okay. However, if you use a Laplace distribution, right? So the full density function is written as follows. Density function is, well, here the density function is proportional to that, right? So I didn't write out the normalization, the normalizing factor, right? So here I'm going to tell you what the normalizing factor is. This is the normalizing factor, 1/2 square root determinant of x sub s transpose x sub s, and then lambda over root pi to the power of s over 2, gamma s over 2, gamma e to the negative lambda L2 norm of x sub s beta sub s. Okay, so you can see this is my normalizing factor, right? And why do I need this guy here? In order to cancel the normalizing factor that I have in the prior distribution for the non-zero entries here. Why do I need to do that? Well, it turns out the normalizing factor here also has an effect or an influence on the model selection property of the base posterior, right? So when you put a prior on the regression coefficient, it turns out you also equivalently put a prior on the model size as well, and the effect is exactly characterized by this fact. Therefore, it is very, very important to cancel out the influence you get from the normalizing factor, so that the correct weight is still this term which is proportional to the minimax rate. But do I need to cancel out this factor? Well, you do not have to, because if you look at the exponent, this is on the exponent is of order s, but here you have of order s log p over s, which is of larger order, right? So this can be neglected. You don't need to correct this factor. But this guy cannot be neglected. Therefore, you have to include an extra factor to neglect it. Okay? So this is actually the best base procedure that you can think of in terms of the theoretical property, right? It is clearly not computable, just as the L0 penalty is not computable. So the next question that we are going to discuss is, can we have any prior distribution that is computable, right? So any prior that is computable. So here is a very famous prior called spike and slab prior. This is very famous. You are going to see that every time you study Bayesian high-dimensional statistics. This is proposed by Edward George. Actually, Edward is a student of Charles Stein. He is now a professor at Wharton. Also one of the previous editor of Annals of Statistics. A very nice person, very encouraging to young people. And with his co-author, also his friend, Robert McCulloch. So this is not Peter McCulloch, this is Robert McCulloch. Actually, the last name is spelled a little bit differently, right? So Robert used to be a professor at Booth, but recently he went to Arizona. I don't know why. Maybe Arizona, the weather is better than Chicago. Okay, so what is a spike and slab prior? Well, the prior can be also described into a sampling process that consists of 3 steps. So in the first step, you sample eta from a beta distribution, beta A and B. Well, these A and B are fixed, okay? So they will be given before you apply this algorithm. And then, given eta, you sample gamma 1 to gamma p, IID from Bernoulli, eta, okay? And in the end, you are going to sample each beta j. Well, conditioning on the value of gamma j, right? So gamma j is going to be Bernoulli, so it is binary. It is either 0 or 1. Okay? So if gamma j is 0, then you are going to sample from a Gaussian with sigma square times v0. Otherwise, you sample it from a Gaussian normal sigma square v1. Okay, you are going to take v0 to be very, very small, and you are going to take v1 to be very, very large, because you use a Gaussian distribution with an extremely small variance as an approximate for the for 0, right? So you sample from that, it is going to be very close to 0, achieve the near sparsity. Otherwise, you just want to sample it from a nearly flat prior. So this component is called a spike, right? Because that's a very narrow density. This is called a slab. So if you if you compare these two prior distribution, they are actually very similar, right? So the first step is always going to control the sparsity, the model size under the prior distribution, right? So in my prior, I explicitly sample the sparsity, but in spike and slab prior, you sample a probability distribution, which then later determines the number of ones that you get in the Bernoulli samples in the second step, right? So in the second step, you can correspond the entries which take ones to the subset S, right? And in the end, you have a spike and slab distribution. Okay, so the reason you can actually sample from this the post distribution if you use this prior, I mean, in terms of computationally, it is really efficient, is because in the end, you have Gaussian distribution, which is conjugate to the Gaussian likelihood. Okay, and the beta distribution is conjugate with respect to the Bernoulli, right? So everything is conjugate. So you can use Gibbs sampling algorithm to solve the computational problem. So in the original paper by George and McCullough, they use Gibbs sampling. But actually, Gibbs sampling is still quite slow. It turns out you can derive efficient deterministic algorithm to sample from the this posterior. So there are two methods. Deterministic algorithms. So the first you can use EM to solve this problem. Okay. Let me write it here. You can use EM. So this is by a very recent paper by Rakova and Edward George. This is actually Veronica Rakova from Booth. So Veronica was a postdoc of Ed George, and this is their joint work. And people also realized that you can solve, you can approximate the posterior distribution by a variational algorithm. Okay. For that, you should check the homework. Now, the spike and slab prior has also been extended recently This is actually a very important progress in the direction of Bayesian high-dimensional regression. And not only that, in my opinion, this is actually the all-time best method in high-dimensional linear regression, including all the frequentist method. Okay, this is the method recently proposed by Yang-So Kim and Matthew Stephens. So Yang-So is my student, and he graduated this year, this quarter actually. He also works with Matthew Stephens' group. This is the method that he did with Matthew in his thesis. So the idea is actually very simple. You still have a Gaussian linear model. Sorry, this is n-dimensional. The prior is really interesting. The prior is going to be sampled from a density function called G sub sigma. Okay, so what is G sub sigma? Well, G sub sigma of t is G t over sigma, right? So this is just scale everything by sigma to have the correct dependence on the noise factor. Okay? But what is this G, right? So this is some function G without the subscript sigma. Okay? So G is the density function of the following distribution. Right? This is a mixture of Gaussian, normal 0, sigma squared k. Okay? And here, pi is a probability. So sum of k from 1 to big K, pi k is 1. Right? So why is this extension of the spike and slap method? Well, if k equals 2, this is exactly the method here. Right? You have 2 spikes. Right? So if k equals 2, then pi 1 is 1 minus eta. Pi 2 is eta. Right? And sigma 1 squared is V0. Sigma 2 squared is V1. So this is like you extend the Gaussian scale mixture from 2 components to k components, right? And what Yang-So and Matthew suggested are suggest to fix the choices of sigma 1 squared, sigma 2 squared, and sigma k squared, right? In particular, sigma 1 squared is going to be fixed at 0, so you always have a spike. But then you use these remaining k minus 2 mixture components to model the slab, right? So it's really a more complicated modeling of the slab. So the idea is if the beta is not 0, then it can come from some arbitrary prior distribution, right? You do not know which prior is true, so you can simply estimate the prior from the data, right? How do you do that? Well, you can estimate the prior by fixing these grids, sigma 1 squared to sigma k squared, and then estimate pi 1 up to pi k from the data, right? So in the end, they show in their paper, actually also in Yang-So's thesis, which I think is available. I encourage you to read it, especially the numerical performances, I think are striking, right? So they show by choosing different pi's, the corresponding shrinkage operator of this prior distribution can not only mimic the spike and slap prior, but can also mimic, for example, the lasso penalty, okay, the L1 penalty, the MCP penalty, scat penalty, elastic net that I didn't talk about, and many other penalty functions. Okay, so in the end, this method, by choosing pies from data, automatically learns the best penalty function from the data. That explains its great performance in practice. And if you look at Young's thesis, he has very comprehensive numerical performances to compare all the sparse linear regression methods in the literature in terms of whether they really work on simulated data, right? So it's very clear all the methods proposed in the literature, including L1, L2, MCP, SCAD, elastic net, they are good at some scenarios and not good at other scenarios. But turns out this method is good and actually is one of the best at all scenarios. So it's really adaptive. Okay. All right. So this is basically everything I want to cover in the topic of high-dimensional linear regression. We started from the very classical AIC, BIC, L0 approach all the way to lasso and Danzig selectors and all the other penalized least square methods. And today we have also learned various Bayesian methods, including spike and slap prior and extension. So now we are going to talk about the last topic for step 302. This is hypothesis test. Well, we have already talked about hypothesis test, but we have only covered the most fundamental simple versus simple situation and how to derive the Neyman-Pearson lemma and how to use that to prove minimax lower bound. And starting from today, we are going to talk about hypothesis tests in more general form. And in particular, we are going to focus on a high-dimensional situation, high-dimensional problems, and the problem of multiple comparison. Okay, since I only have 10 minutes left, I will only be able to give a brief start of this topic. So let me start by a concrete problem, which we have a multivariate Gaussian vector. So the mean is theta, the covariance is identity with dimension n. And let's say we want to test the null hypothesis theta equals 0 against the alternative theta is not 0, right? How do we rigorously study this hypothesis? Well, first of all, we have to be more specific about the alternative, okay? Because if you only specify the null, I can have all kinds of tests, right? So as long as I can control the type of error with significance level 0.05, which is recommended by Fisher for some strange reason, then we claim the problem is solved, right? So it's really arbitrary. However, different tests have different powers, which means we have to understand the behavior, or we can only compare the performance of different tests when we have knowledge about the alternative hypothesis, right? So depending on what kind of alternative hypothesis is, we optimal procedures of testing will be different. Well, the simplest alternative is that it is not 0, and it is going to be away from 0 with a separation given by the L2 loss. Okay, or the L2 norm. So it's either the L2 norm is 0 or the L2 norm is at least epsilon under the alternative hypothesis. Well, in the homework, we have already studied this problem, and I ask you to follow my steps to show that the chi-square test is the minimax optimal test, right? So we have worked with the minimax risk of the testing procedure. Minimax risk. This is just an extension of the minimax risk in for the estimation problem. So let's say let's write a function of epsilon, which is the separation, right? So the minimax risk is defined to be the best test with respect to type 1 error plus the worst case type 2 error. So I'm going to use p theta for this distribution, right? So p theta is a normal theta identity and p0 is normal zero identity, okay? Right, so this is achieved by the chi-square test. With some threshold function that depends on epsilon. Okay, so if you know the value of epsilon, you can actually find the optimal threshold function here, and then as long as you reject the null hypothesis, whenever the L2 norm squared of the data is greater than this threshold function, then you will be able to minimize the worst case testing error, right? So how do we actually achieve? How do we actually prove this is minimax? Well, let me briefly sketch the proof. So first of all, you can actually prove it is an upper bound, right? So this is smaller than or equal to the error introduced by the chi-square test, right? Just take chi-square test here. Okay, and then the type 1 error will be the probability such that a chi-square distribution is greater than this guy, right? And the alternative hypothesis the type 2 error is going to be the worst case probability of. Now, what's the distribution of this guy in the alternative? It will be a non-central chi-square distribution, right? Smaller than the threshold function. Okay? Now, this probability is going to be a monotone function of theta, right? Therefore, when you take sup over theta, the norm of theta is greater than epsilon, the worst case is achieved at the norm of theta equals epsilon. Therefore, this equals this guy plus this guy, right? This is upper bound. Well, lower bound, this is upper bound. In the lower bound, we put a prior on the space of the alternative hypothesis, right? We basically put a prior that is uniform over theta, the normal theta equals pi, right? So, and we just use inequality that the worst case risk is greater than the average risk. Okay? All right, so what is this problem? Now, this is a simple versus simple hypothesis, right? Because you have a prior distribution on the alternative hypothesis. Now, it is as if you test whether the data is generated by the null hypothesis, which is normal theta identity, normal zero identity, or it is generated by the alternative hypothesis. The alternative hypothesis only consists of one distribution. What is that distribution? It is this mixture distribution, right? That's your alternative hypothesis, okay? And we can then use Neyman-Pearson lemma. By Neyman-Pearson, the optimal test here is achieved by the likelihood ratio test. Okay, so it's just a one step. You don't need to prove anything. Just the claim it is the consequence of Neyman-Pearson lemma greater than 1. Okay, you reject if this likelihood ratio is greater than 1. But then in the homework, you go through all the analysis just to show what? Show this is the chi-square test, right? This is equivalent to turns out this complicated statistics is equivalent to this guy greater than some threshold function, right? So you see the lower bound matches the upper bound. You just need to plug in this choice and you can show that. Okay, so fill in the detail if you didn't do the homework correctly. All right, so this is for the chi-square test. And in the next lecture, we are going to study a different problem. We are going to introduce what is called the minimax separation rate. What is the minimax separation rate? Well, it is basically the smallest epsilon such that you are able to do the hypothesis test, right? The smallest epsilon, you are able to tell the difference between H null from H1. Obviously, if H is 0, then you cannot tell the difference because there's no separation, right? So what is the smallest epsilon you can do that? Okay, so turns out the solution will be non-trivial. Okay, so I'm going to tell you, explain the result to you in the next lecture. See you next time.